session. The first speaker is Elie Bou-Zeid from Princeton, who is going to present us on baroclinicity and unsteadiness in wall-bounded flows. So,
thank you, and thank you all for coming to the first early talk in the morning. So we're interested in bounded flows, and usually we consider wall-bounded flows with a constant pressure gradient. I'm going to tell you what happens when this pressure gradient changes in time, or actually with distance from the wall. Okay, so I have to credit the bulk of this work to Mustafa and Khalid. They are the student and postdoc who did most of this work. So we're interested in the atmospheric boundary layer. So this is the bottom layer of the atmosphere where we live and work and produce food. And now increasingly we produce energy there. And in the boundary layer, there are a lot of effects. It's a wall-bounded flow, but it comes with a bit of flavors that makes it a little bit more exciting and complicated. So for example, the atmospheric boundary layer typically tends to be heterogeneous. And that sets up secondary flows that can complicate the dynamics. There are buoyancy effects, stable or unstable. It comes with extreme roughness and topography. So the roughness we heard about yesterday, typically, we're only interested in how it affects the flow above. In the ABL, the roughness is the buildings. So we're interested in what happens even between roughness elements. Also over water surfaces, you can have waves that basically give you moving boundaries, and the thermodynamics in clouds can even complicate it. So it's a wall-bounded flow, but with a lot more complication than what you typically get in your lab. Today, I'm going to focus on two complications that are not yet in this list. So the canonical wall-bounded flow model of the ABL is one that is basically just has buoyancy. So we assume that the horizontal pressure gradient that's driving the flow is constant in height, so that's what we call a barotropic atmosphere, and in time, so it's steady, and the surface is typically homogeneous. So often, for example, you see these observations, I think this is from Colorado, of the wind speed. It goes from 5 meters per second to 20 meters per second in an hour and a half. The typical time of the large eddies here is about 30 minutes, so that's fast relative to the turbulence. And then it decreases, it increases again. So typically, the driving pressure gradient is actually not steady in the ABL. The other simplification is that the surface is homogeneous, so the temperature is constant everywhere. However, most of the real ABLs are heterogeneous. And especially when you have a large-scale temperature heterogeneity, what that can give you is that if you take a column of air with a constant mass that's cold here and hot here, the height of these columns are going to be different. So basically, the isobaric surfaces are no longer parallel to each other. And what that will give you is a pressure gradient that can actually increase or decrease with height, and it can even turn with height. So a pressure gradient that's very different from what you're used to. And the only way to reproduce this in a lab, if you want, is actually to have a vertical channel with a heated or cooled wall. I can tell you, if you're interested, how to make this happen. So today's talk, I'm going to talk about the mean, how to predict the mean of an unsteady flow, and then what happens to the turbulence, and then how to predict the mean in a baroclinic ABL, and then what happens to the turbulence. So let's start basically with the unsteady atmospheric boundary layer. So this is kind of, the framework is that of an Ekman boundary layer where you have turning with height. So Rossby number is important. And this is important for various applications in, for example, wind power generation and prediction, dispersion, as well as, for example, trying to produce closures for weather and climate model where you might need to account for turbulence that's not in equilibrium. So again, the driving question is, how do mean and turbulence behave under such conditions? So we're going to start with a simple Reynolds, the simplest Reynolds average Navier-Stokes for this problem, where the forces that are in action are the pressure, which we're going to express as a geostrophic wind mg. But remember, when you see mg and ug and vg, this is just the pressure, Coriolis and friction. But unlike the Ekman solution, these are not in equilibrium anymore, and so the tendency term remains. So these are the equations for the u component and the v component. V is the other horizontal component, w and z are in the vertical. And the oldest treatment that tried to solve this unsteady system is that of Blackadar, who assumed that at some point, let's say the pressure dies when you go to nighttime, the turbulence dies. And so these stress terms suddenly disappear. And then you can solve the problem starting with initial conditions that are out of equilibrium with what the equations want to go to. This is also the approach that was used by Van de Wiel. Another approach by Lewis and Belcher, Steve Belcher, who's a graduate of the mathematics at Cambridge. What they did is basically they took these equations and modeled nu as a function of z, and they were able actually to solve this equation. This is a very, very nice paper. However, you can only allow nu to vary with z in some limited fashion to be able to get an analytical solution. So we tried to do something a little bit different. We're going to express first the velocity as the complex sum of the u and v component. This is kind of a typical thing that's done in trying to solve Ekman-type flows. And again, this geostrophic wind is just a re-expression of the pressure gradients. And we have a forcing that's going to change in time with a time constant tau f, a characteristic time tau f. And the natural time with which the mean changes is going to be 2 pi over the Coriolis constant, and in our case it's going to be about 12.5 hours. So we're going to do a bunch of simulation where we have very fast variation compared to this, very slow variation or slow variation compared to this, and variability that's kind of has the same time scale as the time scale of the mean flow. And then we're going to do a step change and a linear change in the driving pressure gradient given by UG and VG. So just remember that domain height is 1,000 meters. So if you want to non-dimensionalize thing, just divide the heights by 1,000 when I show things in dimensions. And these are the details of the large eddy simulation code. There's nothing really special or fancy about it. So I'm going to start with case 3, where the forcing time scale was equal to the natural time scale of the EBL. And I'm going to plot the mean wind normalized by the geostrophic wind. So that's the wind very, very far away from the surface. And what we typically observe here, quickly observed, is that actually the velocity becomes super geostrophic. So the ABL is responding fully, the mean is responding fully to every cycle of the forcing. And the wind reach a higher than geostrophic value, which tells you there's some sort of maybe resonance. So, but how do you quantify or explain this resonance? A simple system that shows such behavior is the damped oscillator model. For example, a mass spring damper system that's only a second order ODE that you can solve easily. And so for such a system, the system is underdamped, which means it shows resonance. Only if this constant, if this damping ratio is less than 1. This is what we call the underdamped regime. If it's critically damped and overdamped, it will not resonate or show any kind of oscillation. So how do we prove that there is such a thing happening in the actual ABL? Again, we're going to go back to the initial equations, closed with a eddy viscosity closure. And we're going to take this these gradients, specifically this gradient, and because the time scale of the forcing and the mean is much longer than that of turbulence, we're going to assume that turbulence is in equilibrium, and so we can actually use a log-law type expression for the gradient. And then we're going to replace this by its log-law expression. These are not a function of height. We take them out, and you end up with an expression like that. And then we're going to take this expression and recast it as everything except u. We're going to call this alpha times u. So then these two terms, you can write them as an alpha times a u or times a v in these two equations. And it turns out that it really doesn't matter. Once you cast this as an alpha, you don't care if alpha abides by a log law or not. We can show that if you have a velocity defect law or any other similarity theory, you can write the expression like this, but the alpha is going to be different. So if you let alpha not be constrained by this, you can basically have a more general model. And then you're going to replace these closure models in the main equations. And then when you do this, you end up with these two coupled first order ODEs. Now, for no mathematical reason, so we don't need to do that. It's useless mathematically. But just because it's going to be nice, actually, to illustrate the mathematics, we're going to, or the physics, we're going to take another derivative of these two equations with respect to time. And when you do this, you derive this, and again, the coupling remains there. And when you do this, what's nice is that you can again couple these as a single complex ODE, where A is the U plus IV is the complex version of the velocity vector. And so this becomes just a second order complex ODE. You can obtain easily the homogeneous solution and any particular solution. The particular solution obviously is going to depend on AG and DAG dt. So that's the pressure gradient and how the pressure gradient is varying in time, okay? And this is just something that you can obtain from the initial conditions. And now it becomes clear why we did this, because when you do this, you can clearly see the analogy to a hydraulic damped oscillator model or mass spring damper system, where this is the mass, here 1. The damping is related to the friction, to the viscosity or in turbulence, and the spring is basically related to Coriolis, and what Coriolis is doing is redistributing energy from U to V. So that's kind of kinetic and potential. That's what the spring does. But here it's both kinetic, but in two reservoirs, one is U and one is V. So when you do this, also, if you have no Coriolis, if you're at a pipe flow, let's say small pipe flow, you can just eliminate the spring term and you get a mass damper model. These have to stay. This is the pressure gradient. You can no longer express it as a geostrophic width, so you have to re-express this directly as a pressure gradient, and you can obtain a model, this kind of model, without turning or without Coriolis. Now, how well does that match LES? Surprisingly well. So the solid line are the LES. This is a step change. This is for the step change. So at 24 hours, we double the pressure gradient. So the solid lines are the LES. The circles are an optimized MSD, where the alpha is basically tuned. It's constant, but it's tuned to match the LES perfectly. And in the parameterized PMSD, the alpha is modeled so that you can use this model without running an LES. So you have an actual analytical closure that you can use. So you observe that at these three heights, the optimized model works very well. The parameterized model works quite well at very close to the surface. When you get close to the surface, eventually at larger times, the parameterized model maybe deviates. But the LES is a solution of three coupled partial differential equations. The circles, the model, is a single second order ODE. So the fact that they actually match is quite non-trivial. Okay, with that, okay, so one more example. Again, so what I didn't tell you is that here alpha is constant in time, so even the simplest form of a second order ODE. Here, actually, for some other applications, you need to allow alpha to change in time. The details are here. But this is a test for when you had a step change in the surface temperature without changing the pressure. You allow alpha to be variable. You can parameterize it. And you basically, again, can see the line, which is the LES. Our model, which is our model, this is Van de Wiel, this is Blackadar. So this is our model, the solid dots. And this is the Blackadar model. It doesn't work well. The Van de Wiel model works a little bit better, but ours actually works even better. So this is how the mean responds. Okay, so what happens to the turbulence? So when you need to consider turbulence, you have to add now the time scale of the turbulence. And the time scale of the turbulence is in the ABL is about 1,000 meters divided by, let's say, 0.4, 0.3, which gives you about an hour. The mean responds 12.5 hours, and tau f is whatever you make it to be. So here we have to basically be more careful, because in some cases, if tau mean is much larger than tau turbulence, you're going to get a quasi-steady state turbulence, meaning the turbulence at time t is basically just a function of the mean at time t. However, if tau mean is on the same order of tau turbulence, you can get turbulence that's out of equilibrium, meaning the turbulence, any turbulence statistic is a function of mean at a time t and integrated backwards in time to some memory. And basically, again, what we don't know yet is this tau mean, the response of the mean flow, whether it's going to be characterized by tau EBL or the forcing. So which of these two is going to dictate the actual variability of the mean? So we're going to do some LES. Again, steady forcing, a slow oscillation of the streamwise pressure gradient, the span-wise is 0, a fast oscillation, and a very fast oscillation. Again, compare these to 12.5 hours. compare these to 12.5 hours and to 1 hour, the turbulence time scale. So let's start with the very slow forcing. This is kind of similar to what you had before. The mean goes up and down in phase with the forcing, or almost in phase with the forcing. And if you plot any TKE budget, the TKE or any of its budget term, dissipation, transport, or production, they go up in phase. They go up also in phase with the mean. This is kind of a hallmark of turbulence in equilibrium. And if I had the if I had the idea of asking Mustafa to plot these as a phase diagram, what you would have obtained is something that looks like this. So it's going up and down, but basically along a single line. Okay, so there is no hysteresis in this plot. Now, to basically show that turbulence is in equilibrium, you can also divide dissipation and transport by production, and what you obtain is a somewhat of a constant plot right there. When you go to the very fast oscillation, it was actually interesting because we expected also the mean to oscillate very fast, but the mean is responding as a damped oscillator model, which is also a filter. It turns out that the mean actually filters out the very fast oscillation and only responds very slowly, and in this case, in a decaying way to these fast oscillations that only you see them as these very little wiggles. What happens is the turbulence also decays, and when you try to basically look to see if the turbulence is in equilibrium, it seems to be also in equilibrium because these ratios tend to also remain constant. Now, the interesting things happen when you force with a time scale that's comparable to the turbulence time scale. What happens is you get a mean that oscillates without a regular pattern. The turbulence oscillates with a different pattern than the mean. And then when you plot these normalized TKE budget, you see that the production oscillation and the dissipation production and the transport production ratios are all over the place. And if you were to plot this here, you're going to get probably a plot that looks like, I don't know how it would look like, but it would look with kind of complex and not regular hysteresis. Okay. So this is, again, the interesting one where we have a forcing that's comparable to the turbulence. You see the imbalance between dissipation and production, and you see the mean profile. At some point, you're going to see that even the mean profile is inverted with higher velocity at the surface. Remember, the damping, the viscosity is stronger near the surface than far above. So what will happen is near the surface, the mean flow will respond faster because the stronger damping actually gives you a faster response there. Okay, so this is basically the conclusion of my unsteady component. Let's move on to the baroclinic component. So baroclinicity again happens when you have a temperature gradient. In the barotropic atmosphere, there's not a strong temperature gradient, and the isobaric surfaces are parallel to each other. In a baroclinic atmosphere, they are not, because again, a column of air of the same mass will have different heights, and you get this type of baroclinic environment where the pressure surfaces are angled relative to each other, and so the pressure gradient changes with height. And in this case, you can actually relate how the pressure gradient in the horizontal directions varies with height. You can directly relate it to the horizontal temperature gradient using just hydrostatic equations and mean Rans equations. And in fact, there's a lot of papers that even argue that just the mean pole equator temperature gradient is sufficient to induce non-negligible baroclinicity. So baroclinicity is the default state of the ABL, not the exception. So first, let's just go back to the barotropic for a second and think about the effect of rotation or Rossby number. So if you have no Coriolis or an infinite Rossby number, this is the definition of the Rossby number that we use. So it's inertia over Coriolis forces. You get basically a half channel where the stress decreases linearly with height. But when you start increasing Rossby, the stress decreases faster because now you have the Coriolis force that's starting to act and offsetting the stress pressure balance. So you get a stress profile that's not linear, and you basically can now ask the question, how does the mean wind angle vary as you go with height? So of course, in the barotrop and the no Coriolis case, there's no variation. In all the other cases, you get a wind at the surface that's about 18 degrees oblique relative to the mean pressure gradient, and that can also vary with height. And let's say, what else should I say here? Yeah, I think that's probably all I need to say here. And these two are actually quite intimately related to each other. Okay, here the classic theories tumble when you allow things to become baroclinic. So again, let's say the X pressure gradient increases, or the X pressure gradient decreases, or basically the Y pressure gradient increases or decreases, or both vary relative together. You're going to get much more complex things, and you can basically express this as the height variability of the magnitude of the pressure gradient and its angle as well. In the interest of time, I'm going to have to go a little bit faster. So these are the stress profiles that you obtain for all these baroclinic cases. Don't worry about how they look like. They just look very different from the half-channel flow. That's what you need to know for the time being. And this is really where the classic theory is not only going to stumble but fail. So we're going to also try to derive an analytical expression for the mean flow. So we're going to start with the same equations, but now they are steady. That makes life easier. So we have a mean, the stress vector, because this is a horizontal, this is the projection of the stress tensor on a horizontal plane. So it's just a vector, the pressure gradient, and the Coriolis parameter. And we're going to make an assumption, a strong assumption, that the stress is aligned with the wind. So not with the strain, but with the wind. So it's a little bit of a stronger assumption. Let's see if it works. So if you make this assumption, then you can actually write an expression for the magnitude of tau that only relates it to Fg, the pressure gradient, and the misalignment between the wind and the pressure gradient, or the geostrophic velocity. Notice that the pressure, the alpha g, the angle of the pressure gradient, that's an input, you know that. So Mon and Obukov did something similar, and basically in the end they said that if you want to have a region where you can scale this variability of tau simply like this, so you get a log law, this gives you a log law eventually. Mon and Obukov were smart enough to realize that this will only work for the first 50 meters. And if you go above the first 50 meters, instead of this just becoming a z, this should become an integral of this angle according to our model, and hopefully this will be able to do well even above the first 50 meters. So I'm not going to go very much through the closure, but essentially the closure here is a model for alpha m. So that's your closure. So okay, we do closure. It's all in the paper. I'm not going to dwell too much on it. This is the final closure model. It has the angle alpha of the wind at the surface, and a correction for rotation effects, and a correction for baroclinicity. So you do this, you plug it here, and you integrate, and you get this model for the stress variability with height. And then you say, okay, how well does it match the LES? Greatly in the barotropic, positive shear, and cold and warm advection cases. A little bit more complicated is the case of the negative shear. You can derive a better closure, but still it works well up to almost 100 meters in this case and 200 meters in this case, which would be much better than if you actually neglected or kind of tried to use a Mon and Obukov model. Then you can basically say that tau is just an eddy diffusivity times the gradient of m, and derive a model for the mean velocity m, which is a log law plus a correction for rotation, a finite Rossby, plus times a correction for baroclinicity. And again, you can compare it to the log law and to the LES. Barotropic, it does better because it has a correction for finite Rossby. Great in the positive shear and in the negative shear, even though the stress was not good. I can tell you why. Again, great in all the other cases. So the one thing I want to mention quickly is that this is a free correction. So if you neglect this, you assume this is 1. This is a free correction. You don't need anything except the constant b, which we give you in the paper. So you can use this modified log law even if you want to neglect baroclinicity. If you want to include effects of baroclinicity, you need to know what baroclinicity is doing. Quickly, just a couple of movies about what the turbulence will be doing. This is the barotropic. Typical wall-bounded flow, it's like a channel. You'll be familiar with these patterns. Positive shear, there's strong shear all the way to the top, so stronger turbulence. Negative shear, you have very little shear above, so very little turbulence. And also, if you basically add heat flux, you would notice that the patterns, this is a very strong heat flux, so you expect patterns that look more like Rayleigh-Bénard. But with positive shear, you increase the strength of the shear, so you keep mechanical production dominant. And in negative shear, you kind of it looks like an even more unstable ABL. So I'm going to stop here, just leave these on the board, and ask if you have any questions.
Questions, Rama?
How will all this change in the equatorial region? And what is special about 18 degrees that all the frequencies go there?
Okay, so what's in the equatorial region, of course, there's no Coriolis. So you don't get a balance between Coriolis, pressure, and friction. What you get is a balance between centrifugal force and pressure and friction. So when you get close to the equator, these models will not work, and you need to derive some other models. Now, what's special about the 18 degrees? It's a good question. I don't think anybody has answered that. I think it just tends to be kind of, if you have a wall-bounded flow and you get your typical variability of the turbulence with height. So the Ekman laminar model, which actually not only laminar, it's for any constant viscosity, is going to give you 45 degrees. But because the viscosity is not constant, it changes with height. It seems that the way the viscosity changes with height gives you about 20 degrees in most of the flows and most of the studies. But I don't think there's a theoretical explanation for that. Actually, I mean, I can also tell you that this 18 degrees is a little bit this, is where this B0 comes from. And so, yeah, you can do, this comes from dimensional arguments, but then you need this empirical constant, which is going to give you the 18 degrees.
A question about the viscosity changing with height. Is that just based on the temperature profile, or?
That's not based on the temperature profile. That's based on the horizontal temperature gradient. So what will happen is that so the pressure gradient is the distance between the isobaric planes. If they are parallel to each other, the distance is constant at any height. If they're not parallel to each other, the distance between them varies with height. And so the pressure gradient varies with height. Is that clearer? Okay.
I have a quick question. So the oscillator model that you showed worked very nicely. Could you comment on situations where you don't expect this to match so closely?
Yeah. So I think those would be cases where turbulence is not in equilibrium, and so alpha is difficult to estimate. Either even if you try to tune it from the LES, it will not be constant in time. So you kind of need to arbitrarily say how it varies, and it varies in ways that you cannot, possibly model. So as long as alpha does not vary quickly with time, it probably will work well.
Other question?
Thanks, Elie, for the talk. I was wondering, so did I get it? I might have missed it, but there was the one for the fast fluctuations in the forcing.
Sorry, can you repeat that, Dan? I don't think I listened.
You had a case where you were forcing with a high frequency.
Yeah.
Did I understand that the turbulence decayed after that?
Yeah. So what's interesting about this is that if you go to this case, it's kind of so in this case, what we're doing is just varying the streamwise pressure gradient, and it goes back and forth, right? And so the net forcing is 0, and okay. So the net forcing is 0, and the time is too small to get a lot of energy stored in V. So basically, most of your energy is in U, and it cancels each other, and the mean decays from what we initialize with, and the turbulence decays with it. Interesting, in these cases, it's kind of the same, but in these cases, the time is so long that before you reverse, you basically have enough time to redistribute energy to V. And once you do that, it's not canceled when the pressure gradient reverses. So in this case, you can accumulate energy. In this case, you can't.
Yeah, it's an interesting regime. Have people found it in observations? Is it,
I don't know. So the problem with observations is the pressure gradients are very difficult to measure observationally. I think you could do that, but it's going to probably be more complicated. The variability with time is not going to be a sinusoid or a step change. People see a lot of patterns like this in observations, but I don't think we are yet able to map them nicely to what we have done here. Okay.
I'm sorry, could you
Yeah.
just say why are the pressure gradients so difficult to measure observationally?
Okay, so basically, you need a network of pressure sensors around your tower, if you get that, you get how the pressure gradient varies in time. But if you want to measure baroclinicity, you need towers that are measuring the pressure up to 200, 300 meters. Doable if you have a lot of money for observations. Now, the one thing we have tried, and we've done a little bit of work, is to kind of run some cases with just weather models and look at the pressure gradients from weather models and see what the pressure gradient can look like. But then you need to run a weather model like Prof down to LES scales, which we've done, but it's not a good LES. So yeah, but it's doable.
Speaker again.